Okay, use the following information to answer the next question. Welding is the most common way to permanently join metal parts together. Welders wear helmets fitted with a filter shade to protect their eyes from intense light and radiation produced by a welding light. The filter shade number, N, is defined by the function N equals 7 times, in brackets, negative log of T divided by 3 plus 1, where T is the fraction of visible light that passes through the filter. Shade numbers range from 2 to 14, with a lens shade number of 14 allowing the least amount of light to pass through. The correct filter shade depends on the type of welding. A shade number 12 is suggested for arc welding. Number 7. Let's answer this question. The fraction of visible light that is passed through the filter to a welder arc welding can be written to the nearest 10,000th as 0.0000 AB. The values of AB respectively are blank and blank. Okay, number 7. So I'm going to do this. Let's start a new page. Okay, so this is number 7. Okay, so let's take that equation we have. We have n equals 7 times negative the log of t divided by 3 plus 1. So we said a filter shade. What is that? I think it's called a filter shade. Yeah, the filter shade number, number 12 for arc welding. So we are arc welding. We want to solve for T, which is the fraction of visible light that passes through the filter. So in this example, N equals, let me get the correct term, N equals the filter shade number. Filter shade number. And in this case, N equals 12. That's a given for arc welding. For arc welding. Okay? All right. And then solve for T. And what is T? Let's go back here. T is the fraction of visible light that passes through the filter. So T. Solve for T, which is the fraction of visible light that passes through the filter. Okay, there we go. All right, so let's plug it in. 12. So 12 is my filter shade number, equals 7 times negative log of t divided by 3 plus 1. Okay, so this is a logarithmic equation. Let's solve it. So I'm going to subtract 1 from both sides. I have 11 equals 7. 7 times negative log of t divided by 3. Okay, let's multiply both sides by 3. So I get 33 equals 7 times negative log of t. Divide both sides by 7. I have 33 sevenths equals negative log of t. And then I'm going to divide both sides by negative 1. So I have negative 33 sevenths equals log of t. All right, what are the various ways we have, what are the tools we have to solve a logarithmic equation? Well, one of them is, let's convert it to exponential form. I know this is a base 10 log. This is a common log. So what will I do? I will say 10 to the negative 33 sevenths equals t. So there we go. We can solve directly for t. T is the fraction of visible light that passes through the filter. So let me evaluate this into a scientific notation. So 1.930697729 times 10 to the negative fifth equals T. Okay, so this is dimensionless or unitless value because it's just a fraction of visible light that passes through the filter. Okay, so um, if I convert this to um, just decimal form, that is 0.0001930697729. You get the idea, right? That's T. I'm trying to match the form 0.0000AB. Okay, and let me just check what it says. We're matching the form. Are we rounding at all? Let me just take a look here. Written to the nearest 10,000. So we need to round to the nearest 10,000th. So this is 10th, 100th, 1000th, 10,000th. Okay. And then so let's see. So AB would be 1, 9. So A equals 1, B equals 9. So in our 1, 9. Okay, so let's go back. 1, 9. Okay. Okay, E. coli is a rod-shaped bacterium commonly found in the intestinal tract of warm-blooded animals. Oh, lovely. Okay. Some strains of E. coli can cause serious food poisoning to humans. Suppose a biologist originally estimates the number of E. coli bacteria in a culture to be 1,000. After 90 minutes, the estimated count is 19,500. What is the doubling period of E. coli bacteria to the nearest minute? Okay, so let's take a look at this. Let's go to, this is number 8. Okay, so number 8. So y equals a times b to the t divided by p. Okay, this is our exponential growth equation where p is the doubling period and b equals 2, okay, because we are talking about doubling period. So a value is 1,000 bacteria count, okay? The y value, the final, is 19,500. So let's plug it all in. So we are looking for, the time is 90 minutes, right? So we know that time is 90 minutes. So when I plug this in, 19,500 equals initial amount. So this is the final amount. 1,000 is the initial amount. Okay. And then times b value is 2 because we're talking about doubling period. 90 minutes divided by p. So remember, since this is in minutes, you're going to get a return of a p-value that's also in minutes. So be careful. And the question is asking the answer in to the nearest minute. Okay, so we're good. So when we do this calculation, we can be assured that the final answer is going to be in the correct units. Okay, so when I evaluate this, I'm going to divide both sides by 1,000. So that's 19.5 equals 2 to the 90 divided by p. Okay, you can take the common log of both sides, or let me convert this to logarithmic form, which will bring the exponent down. So that's log. I take the base of the exponent, which is 2, log base 2. The argument is 19.5, and that equals the exponent, 90 divided by p. Okay, multiply both sides by p. I get p log base 2 of 19.5 equals 90. Divide both sides by log base 2 of 19.5. So P equals 90 divided by log base 2 of 19.5. Okay. Evaluate that with your calculator. I get a p-value of 21 minutes. What does that mean? Let's make a sentence. The doubling the doubling period of E. coli is 21 minutes. Well, what does that mean in plain speak? So it takes 21 minutes for E. coli bacteria to double its population, or its count, whatever you want. So its population. Okay? All right. Number 9. On April 26, 1986, a nuclear reactor located at Chernobyl, USSR. So that's the Soviet Union. That's before Russia, right? A nuclear reactor located at Chernobyl, USSR, exploded, causing the worst nuclear accident in history. This actually happened in, I know it says USSR, but where the Ukraine is, right? So it's a town in Ukraine. Okay, one of the radioactive isotopes that was released into the atmosphere was iodine 131, which has a half-life of approximately 8.1 days. Determine algebraically the length of time to the nearest day that it took for no more than 1.5% of the substance to remain in the atmosphere. Okay, exponential decay. So let's go to number 9. I'm going to start a new page here. Number 9, folks. Number 9. Okay, so y equals a b to the t divided by p. We want to know how much time it took for 1.5% of the original radiation to be left over. I think that's what it's asking. So let me just make sure. 1.5% of the substance to remain in the atmosphere. So remember when we did these kind of problems, right? It doesn't tell us how much we start with. It's just that I want 1.5. How long does it take for 1.5% of the substance to remain? So I can say that the initial amount, A is initial amount. You can either start with 100 or 1, right? So let me do 100. A is initial amount, which can be represented as 100. I think when we use whole numbers like this, it's just easier to think about it and do the calculation. So that y is the final amount. If we said 1.5% of the original amount, so y is the final amount, which can be represented as 1.5. Okay? So I have my A value, I have my Y value. B value, I'm going to say B value because we're talking about half-life. B value is half-life is related to half-life of iodine 131, the radioactive isotope. So B equals 1/2. Okay. P is the, not doubling period this time, halving period. So how long does it take for half of the substance to decay away? Or, said another way, how long does it take for half of the substance to remain? So P is the halving period, and we defined it as 8.1 hours. Oops, no. Hang on. Let me just, not 8.1 hours, 8.1 days. Sorry about that, folks. So let's correct that. 8.1 days. Okay, let's go down. Okay, so let's take a look at our formula. So y is 1.5, the final amount. A is the initial amount, we said is 100. B is the halving period, so 1/2. T is the time that it takes to reduce to 1.5% of the original amount, and then divided by P, which is 8.1 days. Okay, so let's divide both sides by 100. That's 0.015 equals 1/2 raised to exponent t divided by 8.1. This one, let's do log base 1/2 of the argument 0.015 equals t divided by 8.1. Multiply both sides by 8.1, so I have 8.1 log base 1/2 of the argument 0.015 equals my time value. Okay, so since the p-value is in days, my t-value, when I evaluate this, it says to the, what's my rounding? What am I going to? To the nearest day. So we want it to the nearest day. So nearest day, that would be 49 days. Okay, let's just write a quick sentence. What does this mean? It took 49 days for radioactive iodine 131 to decay to 1.5% of its original starting value, Okay, that's number 9. All right. Number 10, earthquake time. Okay, let's read this box here. It says, use the following information to answer the next 3 questions, okay? The Richter magnitude, capital M, of an earthquake is defined as M equals log of the ratio of A divided by A naught, where A is the amplitude of the ground motion, usually in microns, measured by a sensitive seismometer, and A naught is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. An earthquake in Turkey in 1999 measured 7.4 on the Richter scale. An earthquake in Seattle in 1996 measured 5.3 on the Richter scale. Determine algebraically how many more times as intense was the Turkey earthquake compared to the Seattle earthquake to the nearest tenth. Okay, let's take a look here. I know in our notes, we converted this equation to the equation where you can compare both earthquakes. You can do it that way. That's a quick and easy way where you just plug it in and you're done. The way I'm going to do it is in 2 separate ways. So let's do number 10, next page. Okay. So number 10. First, the Turkey earthquake. So earthquake in Turkey. Magnitude 7.4. Okay. Well, first we're using this equation, folks. M equals log of A over A naught. Okay, so 7.4, that's the magnitude of the Turkey earthquake in 1999, equals log of A divided by A naught. Okay, let's convert to exponential form. That's 10 to the 7.4. Remember, these are common logs, right? This is common log with a base 10, right? So that's why I can convert it as such. Okay, 10 to the 7.4 equals A divided by A naught. Okay, so this A value is the intensity measured in microns of the earthquake in Turkey. So A Turkey equals 10 to the 7.4 A naught. Okay, how about Seattle? That is 5.3 magnitude on the Richter scale equals log of A divided by A naught. Okay, that's 10 to the 5.3 equals A over A naught. Okay, so I'm converting to exponential form. And then this is the intensity of the earthquake in Seattle measured in microns. So that is A Seattle, the intensity of the earthquake in Seattle equals 10 to the 5.3 A naught. Okay, last part here, we calculated the intensity of the Turkey earthquake and the Seattle earthquake, and we want to compare how many more times intense is the Turkey earthquake compared to the Seattle earthquake. So intensity of the Turkey earthquake compared to the intensity of the Seattle earthquake, that is 10 to the 7.4 divided by 10 to the 5.3. Okay, and both have the A naught value. These divide out to 1, so when we do the final math here, I get 125.9. Let's make a statement about that. So the earthquake in Turkey is 125.9 times as intense as the earthquake in Seattle. Ooh, Seattle. Okay, there we go. That's number 10. Let's go to number 11. So number 11, an earthquake in Quakerville is 300 times as powerful as the one in San Francisco. If the earthquake in San Francisco had a magnitude of 6.5, algebraically determine the magnitude of the one in Quakerville to the nearest 100th. Okay, so let's see. Number 11, folks. Okay, the equation is m equals log of A divided by A naught. In San Francisco, .5 magnitude equals log of A divided by A naught. Okay, convert to exponential form, 10 to the 6.5 equals A divided by A naught. Okay, so this is intensity of the San Fran earthquake. So A San Francisco, the intensity of the San Francisco earthquake equals 10 to the 6.5 times A naught. Okay. Um, in Quakerville, so let's do Quakerville. Okay. Intensity of the Quakerville earthquake. Okay, it says 300 times, right? So let's go back here. Earthquake in Quakerville is 300 times as powerful as the one in San Francisco. So how do we set up this equation? Intensity of the earthquake in Quakerville is 300 times the earthquake in San Francisco. Okay, so we're just doing a substitution there. All right, so let's evaluate. So the intensity of the earthquake in Quakerville equals uh, well, let's leave it like this because we'll plug it in this way. Okay, so if I have the equation, we need the magnitude. What's the magnitude of the earthquake in Quakerville? So magnitude of Quakerville earthquake, that is log of A divided by A naught. Okay, so magnitude of the Quakerville earthquake is log of, uh, this entire thing is my A value on the top, so that's 300 times 10 to the 6.5 A naught divided by A naught, which is our reference earthquake. Okay, so the A naught values will divide out to 1. So what am I left with? Magnitude of the Quakerville earthquake is equal to the log of 300 times 10 to the 6.5. Okay, evaluate that, and what do I get? The magnitude of the Quakerville earthquake is 8.98. Okay, so what does that mean in words? The earthquake in Quakerville has a magnitude of 8.98 on the Richter scale. All right. Last one, folks. Number 12. An earthquake with a magnitude of 5.0 on the Richter scale is 50 times more intense than one of its aftershocks. Determine the magnitude to the nearest tenth of the aftershock algebraically. Okay, so we're going to do this in much the similar way as we did number 11. So number 10, sorry, this is number 12. M equals, so here's our equation for earthquake magnitudes. So the original earthquake is 5, magnitude 5 on the Richter scale. Okay, convert to an exponential form. Okay, and then so let me just go back real quick. Yeah, that's the original earthquake, the magnitude 5. So that is A equals 10 to the 5th A naught. So this is the original earthquake. And then we're going to compare it to the aftershock earthquake. Okay, so original earthquake, not magnitude, intensity, right? Intensity. Okay, so what's next? So we have that A value. Let's look at the aftershock. So aftershock. Aftershock is just, it's another earthquake. Literally, it's another earthquake, just of smaller magnitude, right? So A, and let me call aftershock as AS, equals, it says 1/50th of the original. Okay, so 1/50th of the original, which is 10 to the 5th A naught. Okay, so if I use my equation, I want to find the magnitude of the aftershock. That's m equals log of the ratio of a divided by a naught. Okay, let's plug in our value. This entire thing is my a value, so that's 1/50th times 10 to the 5th a naught divided by a naught. Okay, the two a naught reference values divide out to 1. So magnitude of the aftershock equals log of 1/50th times 10 to the 5th. Okay, and then that is the magnitude of 3.3. So what does that mean in words? The aftershock, the aftershock has magnitude spelling magnitude of 3.3 on the Richter scale. Okay, and that is the last one. So we are done.